Okay, so what we're going to cover today is we're going to start with the derivative as rate of change. And while we're talking about the derivative as a rate of change, we'll also talk about how the graph of a position time graph relates to the velocity and the acceleration of the vehicle or the particle that's moving back and forth along a linear path. And we'll talk about where it's speeding up, where it's slowing down, and how that relates to the velocity and the acceleration on the graph. So that's basically what we're going to be looking at for derivatives as rates of change. And we're going to start with the amount of change formula. So let's take a look at the amount of change formula. This is something we're going to see later this semester as well. Towards the end of the semester, at the end of, I believe it's chapter 4, we talk about what's called the linear approximation function. And the linear approximation function is really just the tangent line itself, all right? So we're looking at the tangent line at a point. And what the idea behind this is, as long as you make the change very small, then the tangent line is a really good approximation for what's happening on the function, as long as you stay really close to the point where they touch. So if you stay really close to this point where they're connected, then you can use the value on the tangent line to approximate the value on the curve, because they'll be relatively close together. So the idea is to use the tangent line as sort of this approximation. Now, what we're getting at here is the change in the y value. So this f of a plus h minus f of a, that's the change in the y value on the actual function itself between 2 points. So if we're looking at the point where they connect and we're looking at a point over here, it would be the difference in the y value between the 2 points on the actual curve. But we can approximate that with the point on the tangent line. Now remember that this formula, the difference quotient, is basically just the slope of the secant line. And the slope of the secant line gives you the average rate of change, the average amount that the y values are changing with respect to the x values. So the average change. The instantaneous rate of change is given by taking the limit of the difference quotient and allowing the denominator, the distance between the two x coordinates, to go to 0. And that will give you the instantaneous rate of change. And again, as long as we stay relatively close to the two, to the point where they connect, we can use the slope of the tangent line to approximate the slope of the secant line. So again, what we're talking about here is having some curve like this and having a point where we have a tangent line. And we're going to have a point here and a point here. It's almost hard to draw where they're so close together. All right. So we have 2 different points there. And we've got a slope of a secant line which connects these 2 points right here, but they're so close together that we can use the slope of the tangent line to approximate them. So this is called the amount of change formula, and it comes from solving the equation for the y value. So the y value f of a plus h can be approximated. We just multiply both sides by h, and then we move the f of a over by adding it. So what we're saying is the y value on the function can be approximated with what amounts to the tangent line equation. This equation right here is really the tangent line at a. So we can approximate the y value at another point that's really close by, as long as we don't allow h to get very large. And the tangent line is a decent approximation as long as you stay very, very close to point A. And that's all they're doing right here. So let's take a look at one of what one of these would look like. So this is the average rate of change for very small h. Here's a better picture than I'm able to draw. It's kind of blown up rather large. So you can see the tangent line is coming through here. And they had to draw the point further away than you would really use it. You would really use the approximation probably in this section right here. On the graph, you would probably use it between these points and these points. Because in those points right there, do you see how closely the tangent line skims along the curve? So that's what we mean by keeping h small. And if we kept h small there, then we can approximate the value on the curve, which might be some really difficult function, with the equation of the tangent line instead. And the equation of the tangent line, well, it's a line, so it's relatively simple. So we're using the y value there on the tangent line to approximate the y value on the function. So our formula, again, is that f of a plus h is approximately equal to f of a plus the derivative at a times the small distance you move over. Right here, this is at 10. This is at 10.1. So our h value is 10.1 minus 10, which is 0.1. That's what we mean by a small amount. All right, so we've moved over just a small amount. All right. F of a is given to us. F of a is given to us as -5. And we're also given the slope at the point 10, x equal 10 as 6. So we can use this part of the formula to approximate f of 10.1. It's going to be approximately equal to -5 plus 6 times the 0.1, which is going to be approximately -5 plus 0.6, which is approximately -4.4. All right. So again, all we're doing is we're using the slope and the point where the two graphs connect, and we're writing the equation of the tangent line, and we're using the tangent line to approximate the value on the function. All right. Okay. All right. So motion along a line, rectilinear motion. This is probably the most difficult part, and this is the part that's not really well explained in the book. All right, it does go through it, but it's not very well explained. So I want to spend some time talking about what rectilinear motion means and what the equations come out and how they relate to the motion of the particle and how they relate to the graph. So we actually have all these different relationships here. If we let s of t be a function giving the position of an article at time t, then the velocity is given by the first derivative of the position function. So derivative of position gives us velocity. Then the speed of the object is given by the absolute value of velocity. Velocity is actually a vector. It has both direction and magnitude. So when you say velocity, you can't just say 60 miles per hour. That's speed. You have to say 60 miles per hour north or 60 miles per hour west. You have to give a direction as well associated with the velocity. The acceleration of the object is the derivative of velocity and the second derivative of position. So acceleration is v prime or s double prime. That's how we say that, s double prime. There's actually something called the jerk. And the jerk is that sense when you're in a car and somebody slams on the brake or they slam on the accelerator and you get that motion where you're jerked backwards or you're jerked forwards by the motion of the car. That's the jerk. All right. It's well named, right? So it turns out to be the derivative of acceleration. So it's the second derivative of velocity and the third derivative of position, or v double prime and s triple prime. right? Okay, so let's talk about this particular graph right here, t squared minus 5t plus 1. This is going to graph the position of a particle moving on a coordinate axis running horizontally. Its position is given by that, but the motion of the particle itself is back and forth. So the particle itself is going back and forth and back and forth and back and forth. So the particle starts, there's an origin somewhere. Oops. And then the particle starts somewhere and it moves one direction and then it comes back and then it moves and then it's just going back and forth on this line. That's what the particle is actually doing. The particle is traveling in a linear motion, so in a line. But the position of where it is on the line in relation to the origin is given by that equation that we had a second ago. I think it was t squared minus 5t plus 1, I believe. Yeah, t squared minus 5t plus 1. All right. So when we're looking at this particular graph, we want to think about how all of this relates. This is our position right here. This is s of t. And this axis is the time axis, or t. All right. So let's talk about the different things that we can note about it based on where we are. First off, if it's in a negative position or a positive position, what does that mean? So notice that it starts out up here at 1. The origin corresponds to this spot here on the linear path that it's traveling on. Think of it as being on an interstate road where it can only go east or west, right? So it's going back and forth, east or west, or you could draw the line vertically and then it could go north and south. But for now, we'll do east and west. So it's only traveling back and forth along this interstate, but the origin is here. But our particular graph, when we're looking at it, it starts right here at the 1. What does that mean? That means that when time starts, it's not at the origin. It's over here, a distance of 1 away from the origin. So it might be something like 1 mile. Well, the question is it east or is it west? A positive position in this case is going to mean to the right of the origin, and a negative would mean to the left of the origin. So our thing can actually travel past the origin and go on the left side and then come back and then go back and forth. But the origin is here in the same place every time. Okay, so what does that mean? If it is in a positive position, then that means that it is to the right of the origin. And if we're on a left-right graph, we'll call that east. If we're on a north-south graph, we would call that north. Right? So it starts out to the right side of the origin, but then when it's traveling, notice that it goes below the axis, below the t-axis, and that means that its position is now negative. And so if it has a negative position, it's gone to the left of the origin. And on our graph, we'll consider that to be west. If you are on a vertical graph, you would call that south. All right. So now we know what it means to be above the t-axis and below the t-axis. If we're on the t-axis, then we're at the origin. So if we're on the t-axis, we're at the origin. So for example, if we want to consider this to be Interstate 70, all right, then we could make, well, 70 doesn't go through downtown, but we'll pretend and say that it does. All right. So 70 could be the intersection of, well, let's just say that the origin is the intersection of 70 and I-25. All right. So if you're on the t-axis, then you're there at that intersection of 70 and I-25. If your position is positive, you're east of that intersection. And if your position is negative, you're west of that intersection. All right. Now let's talk about the slope of the tangent line and what that means. The slope of the tangent line is the velocity. All right. So let's take a look at our picture, and we can use our pen as sort of the tangent line. So put your graph on there. You can tell that on the first part of the graph, from t equals 0 to about t equal 2.5, something like that, until we get over to there, it looks like the slope is negative. So since the slope is negative, that means that the velocity is negative. So if the slope of the tangent line is negative, it's headed in the left direction, or in our case, west. So we have the slope of the tangent line negative, then it's headed west or left. And if you're on a north-south graph, then it would be headed south. All right. So what does that mean if the slope of the tangent line is positive, like between, say, 2.5 forever after that? Well, if the slope of the tangent line is positive, then it is headed towards the right, which would be towards the east. Now, this doesn't mean it is east, it just means it's traveling east. All right. And if you were on a north-south graph, this would be going north. Right? Okay. And none of this information, I'm afraid, is actually in the textbook exactly. It's there. It's just, it's hard. You kind of have to know what you're looking for in order to pull that information out. So what does it mean then for the article to be right here at 1? At 1, we have a spot right here. The position of it is negative because it's below the t-axis. So it is on the left side or the west side of the intersection of I-20, I-25 and I-70. And the slope of the tangent line is negative. So it is still headed towards the west. It's still headed left. It is to the west of that intersection and it's headed west. All right. And then what happens right here when the slope of the tangent line is 0? What does that mean? The slope of the tangent line is the velocity. So that means that it's stopped. In other words, it could be making a U-turn, right? So it stopped, came to a stop here, because the next thing it's going to do at, say, 4 is it's going to be changing direction. Now, where is it at 4? It's still a negative position. So it's still west of the intersection of I-25 and I-70. So it's still out in, I don't know, let's say Arvada or somewhere like that. So it's still to the west of that intersection, but it is traveling. Notice that the slope of the tangent line is positive. It's traveling east. So it's headed east towards Aurora or the airport, but it is west of the intersection until it reaches just shy of 5. At just shy of 5, it reaches the intersection, but it continues to travel towards the east forevermore. All right. So let's talk about some more things that we can note then. This means that at maxes and mins, it's stopped. All right. Now, what does that mean? Well, that means that on the left side of a max or a min, it's got to be slowing down. Why does it have to be slowing down? And by slowing down, we are talking about the car slowing down. We are not talking about deceleration. Deceleration is a physics concept, and it has to do with the rate of change of acceleration becoming smaller. So that's not necessarily what's happening. The acceleration can be increasing and it still be slowing down. It has to do with whether or not the velocity is positive or negative. All right, so be careful. Deceleration and acceleration are slightly, I know this gets to be a little crazy. All right, but slowing down is what the car is actually doing. Why does it have to be slowing down on the left side of a max or a min? Because it's about to stop. All right, and that's what cars do right before they stop. On the left side, it's slowing down. So what do you suppose it's doing on the right side of a max or a min? Speeding up. It's got to be speeding up. So on the right side of a max or a min, it's speeding up. Now, there's another piece of information to put on here. Well, there's several more. One has to do with the acceleration. When do you know it's accelerating and when do you know it's decelerating? So acceleration has to do with the concavity. So if it's accelerating will be positive, then it is concave up. Positive acceleration. Which is not always what we mean by putting our foot on the gas pedal. All right, that is not what I'm talking about. All right, that is speeding up. All right, so you need to separate and unlink those two ideas in your head, because what we call the accelerator is not the accelerator, it's the speed upper. All right, it speeds you up, and the brake slows you down. All right, the acceleration has to do with the rate of change of the velocity. So if the rate of change of velocity is becoming positive, then it is accelerating. So in fact, it is accelerating over this entire interval. Now, why would that be? Let's think about the value of the slope here. So let's put on some numbers for the slope. It's traveling 70 miles per hour in the west direction, then -60, then -50, then -40, -30, -20, -10, and then it stops right here. So I'm looking at what the slope is doing as I'm coming towards this place where it stopped. If you were to take the rate of change of velocity, you would get a positive, because if you take a -50 and you subtract a -60, you get a +10, right? -50 minus -60, you have a double negative, so it becomes a +10. So it is accelerating because it's becoming less negative. I know that sounds crazy. All right. I know it sounds crazy. I'm sorry, it's physics. So as it becomes less negative, it's actually accelerating. Now it's easy to tell it's accelerating on the right side because it starts off with 10 and 20, then 30 and so on. But in fact, it's accelerating the whole way. because the velocity is becoming less negative, which means the velocity is increasing in value. Negative 50 is larger than negative 60. Negative 40 is larger than negative 50. So it is accelerating. The rate of change of velocity, which is acceleration, is positive the whole way. Now, if that still is hard for you to grasp, don't panic, because you can do these problems without having a firm grasp on that acceleration, deceleration. All you need to know is that the shape of the curve tells you whether the acceleration is positive or negative. If it's up like a cup and holds water, it's positive acceleration. If it is concave down like a frown, then it is negative acceleration, which is what we call deceleration. All right. Okay. Let's take a look at another one. Now, remember, of course, that this is just the graph of where the position is with respect to time, but the car is just traveling east and west on I-70. That's all the car is doing. The car is going back and forth in a line. Okay. All right. So let's see, where am I now? I think all that is explanation. Explanation. All right, we're going to get to inflection points. The last graph did not have an inflection point, but this graph does have an inflection point. You can see here that it is concave up on the left side. So this part right here is concave up. And this part over here is concave down. All right, it's usually pretty obvious when they're one way or when they're the other. It's concave up like a cup, so it holds water, or concave down like a frown, it does not hold water. All right, concave up means the acceleration is positive. All right, so over here, concave down means the acceleration is less than 0. All right. What happens somewhere in between the concave up and the concave down is a single spot that's called the inflection point, where it changes the curvature. We call this the curvature. And when it changes that point right there, what's happening is you are not speeding up and not slowing down. The acceleration at the inflection point is 0. Because if it's positive here and negative here, and it's a continuous function, by the intermediate value theorem, what do you know it has to do? If it's positive here, negative here, and it's continuous, somewhere in between, the acceleration has to be 0, right? So that's the intermediate value theorem. And right here at the inflection point, the acceleration is 0. You can think of this as not braking and not accelerating in the car. So your foot is not on the gas and your foot is not on the brake either. It's a moment where you're coasting, all right? So you're not speeding up and you're not slowing down, you're coasting, maintaining velocity. And because you're maintaining the velocity, then that means that your acceleration is 0. Okay, now there are some ways of knowing from the graph whether you're speeding up and slowing down, but I found that for most students, it makes more sense to them that you have to slow down before you stop. So the left side of a minimum or the left side of a maximum, you've got to be slowing down. So we're slowing down in this region and slowing down in this region. So let me put those pieces of information on here. So on this section right here, We are slowing down because we're about to stop. And on this section right here, we're slowing down because we're on the left side of a place to stop. Now, what about in this region right here and in this region right here? In those two regions, we are speeding up. Now, that doesn't mean anything as far as velocity. Velocity could still be positive or negative. This means your foot is on the gas. All right? Velocity is not the accelerator in the car. Velocity has direction associated with it, which gives it a positive or a negative sign. All right? You have to be speeding up after you were just stopped because you got to get moving again. All right? So notice that when you're speeding up, if you take the product of the sign of the first derivative and the second derivative, you'll get a positive. All right, that's one way of doing it. If you take the sign of the first and second derivative, the velocity and acceleration, and multiply them together, you get a positive. That's one way of knowing it's speeding up. I prefer doing it based on position on the graph. If you're on the right side of where you were just stopped, you're speeding up until you get to an inflection point. The inflection point, so basically you've got your foot on the gas in the yellow section, you hit the inflection point. At the inflection point, you take your foot off the gas pedal, but it's not on the brake pedal yet. In the gray section, you put your foot on the brake pedal, and it's on the brake pedal till you come to a stop. Then when you're stopped, you take the foot off the brake, and then you put it on the gas pedal again. And in the yellow section, you've got your foot on the gas pedal. All right. The velocity is negative here because you are headed west. All right. Not because you're braking. All right. Does that make sense? So another way of saying slowing down is you're braking, and this is pedal to the metal. All right. Okay. So hopefully this makes sense. Are there any questions over what we've talked about so far?
Can you just really quick go over the definitions of speed versus acceleration versus velocity again?
Yes. Okay. So speed is the magnitude of the velocity. But when we say speeding up, we mean literally putting your foot on the gas pedal. All right. So the foot on the gas pedal. But if the foot's on the gas pedal, you could be traveling east, which is the positive direction, which would make it this direction here on the left. Or you could be traveling west, which would give you a negative slope. All right. So the velocity would be negative, but you're still speeding up in the negative direction. You're speeding up going west. All right. So you're getting negative 10 miles an hour, negative 20, negative 30, negative 40, negative 50, negative 60, negative 70. Who knows how fast you go on I-70? Depends on whether it's the weekend and we've got lots of tourists, right? So again, this is traveling in the negative direction. And so the velocity is negative, but it is increasing in magnitude. So negative 10, negative 20, negative 30, negative 40, negative 50, they're getting smaller in their value, but in absolute value, they're getting larger. So it is speeding up. All right. Over here, it's traveling in the positive direction. So 10, then 20, then 30, then 40, then 50. It doesn't matter whether you do absolute value or not because it's headed in the positive direction, which is east. So you can think of it basically like a number line. And east is positive and west is negative. All right. And then the origin is wherever you declare it to be. I declared it to be the intersection of I-25 and I-70. All right. Now, acceleration is the rate of change of the velocity. So let's talk about this one right here. The acceleration is negative because as it changes, it's becoming more negative. Does everybody see that? The amounts that you're traveling here would be like -10, -20, -30. These are your velocities, -40, -50. So if you took -50 and you subtracted -40, your rate of change would be a -10. So your acceleration is negative. Remember, your acceleration is going to be the rate of change of your velocity over however long it's traveling. Right? So it took it 1 second or whatever. Then it would be a -10. So it's negative. Over here, they're positive. So 10, then 20, then 30, then 40, and so on. So when you do the acceleration over here between 2 points 1 second apart, you've got 40 minus 30 over 1, which gives you a positive acceleration. Now, I don't do it that way. When I look at it, I just go, oh, it's concave up, positive acceleration. Concave down, negative acceleration. All right. Okay. Let's try another example. We're going to do a couple of examples of this. So let's try an example. We have some questions to answer about this graph right here. So I'll copy off the graph. Use the graph of the position function. So this is position versus time to determine the time intervals when the object is to the left of the origin and to the right of the origin. So left of the origin would be west and right of the origin would be east. So again, the particle itself is traveling on an east-west road. Somewhere there's an origin. And all the particle is doing is going back and forth across the road. All right, so it's just traveling forwards and backwards, speeding up and slowing down. All right, going back and forth. All right. So when we look at the graph, remember that this is our position and this is our time. So when we look at it, notice that the entire graph is above the t-axis. There's no point on this graph that comes below the axis. The position is never negative. If the position is never negative, then it's never going to be to the west of the origin. It's always to the east. All right. So it's always to the right of the origin. All right. Above the axis on the right side, below the axis on the left side. That's position. All right. Above the axis to the right, below the axis to the left. Now we want to look at probably the slope of the tangent line for our second question. Use the graph to determine the time when the object is at the origin. At the origin means it has to be on the t-axis. And there's really only one time that it's on the t-axis, and that's right here when time equals 0. So the only time it's on the axis is at t equals 0. All right, and that's the answer to the second question. All right, that's the only time that it hits the axis, which is not surprising because it spends all the rest of the time to the right. All right, so in other words, for our car traveling east-west on I-70, it is always, it starts out at the intersection of I-25 and 70, and then it spends the whole rest of the trip on the east side. All the rest of the trip is on the east side. It never goes west of that intersection. It never comes back to that intersection. All right. So looking at it, it travels away from the intersection, then it comes back towards the west for a short section. What's happening here in this part right here, where we have this horizontal line? Slope of the tangent line would be 0. What does that mean? What did the car do?
It stopped.
It stopped. Right. It stopped and it's not moving. So it took a break. Maybe they had to stop at a 7-Eleven or something and get some coffee or whatever. But the car is not moving right here. So for this period of time between 2 and 5, the car is not moving. Then it starts moving again and it's moving towards the west, and then it stops again, and then it starts moving east again. All right, so it's moving east, 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 stops, comes back west for a little bit, stops for a long period of time, then it travels towards the west, but it doesn't reach the intersection. It's still on the east side of the city. And then it turns around, stops and turns around and heads back east again. Right? That's what the car is doing. All right, so now we want to figure out the time intervals when the velocity is positive, negative, and 0. So when the velocity is positive, then it's headed towards the east. And that looks to me like it would be between 0 and, we're going to call that 1.5 maybe. All right, so from 0 to 1.5, the slope of the tangent line is uphill. Then it goes downhill, so that's not positive. Then it's stopped, then it's headed west, so that's not positive. But then right here, it goes back positive again, so that's where it's headed east again. And I would say between 6 and 7. All right, so it's positive and headed east, and those two time intervals. When is it negative? If it's negative, it's headed towards the west. It doesn't have to be west of the intersection. It's just headed in the westerly direction. So when we're looking for this, we're looking for a negative tangent line. So we have a negative tangent line here between about 1.5 and 2, looks like, between 1.5 and 2. And then we have another section after the car is stopped for a period of time, it heads back west again. So that's between 5 and 6, it looks like. And then the last one it asked about is when is it 0? And when it's 0, it's stopped. So we have 2 single instances in time. At 1.5 and at 6, the car is stopped for that one single moment in time. I mean, if you're going to turn around, the car has to be stopped at one instant. It can't travel this way and then travel back the other way without being stopped at one instant in time. And then we have this long stretch in the middle where it stopped between 2 and 5. Okay. What's the next question that it asks us? The next question says, use the graph of the position to determine the time intervals when the object is moving left, moving right, or is stopped. Well, we kind of have already done that because we did the moving left, moving right, and stopped. So we've already got those written down up here. It stopped at 1.56 and between 2 and 5. It's headed west, which is to the left at between 1.5 and 2 and between 5 and 6. And it's headed to the right or east between 0 and 1.5, and again between 6 and 7. So we've already answered that question when we did the previous question. Right? The next one is a little bit more difficult. The next one says, sketch the graph of the velocity. So this is basically one of those, sketch the graph of the derivative on the function. All right, so we were practicing that in class yesterday and the day before that. And now we want to practice it on this one. Remember that sections that look like parabolas, their derivatives look like lines. So what we want to do is we want to just estimate. It's not going to be exact. It's an estimation of what the overall shape of the derivative looks like. It's not going to be perfect. But again, we're going to start out by saying it's a steep uphill line. So that's got to be a large positive number. And then as it slows down, that means the velocity is becoming smaller in value. So the velocity derivative is getting close to the axis here. And right above 1.5, it's going to stop and hit the axis. So we would have an x-intercept directly below that spot. So we can draw our x-intercept for the derivative right here. And it's going to be coming down like this. And then it goes a little bit negative. So in this section, notice how it turns just slightly tilted downhill, then more downhill, then more downhill until it stops. So we have a small section here between 1.5 and 2 where it continues with the velocity being downhill. So we have a section like that. And then do you see how this is a corner here at this particular spot? This doesn't connect in a smooth way. So we're going to draw a hole here at the bottom to indicate they don't connect in a smooth way. They connect at a sharp corner. Derivatives don't exist at sharp corners because there's no way to get a unique tangent line balanced on a corner. Then what about this section where it's straight? It's a horizontal line. The slope of it is 0. So we're going to have a section where the velocity is 0 sitting on top of the axis. So we're going to have a section, and I'll make it heavy and dark. Oops, I went a little too far. Up to the 2. And up to the 5. And again, we put zeros at either end because we've got corners at the 2 ends there. All right. Now this is another parabola. So the derivative is going to look like a line. It starts out negative, very negative. So it's going to be down here below the t-axis. And then as it is slowing down to stop, it becomes less negative, which means it gets closer to the axis. Then at 6, it hits the line. And then it tilts positive, and then it increases and keeps going. So directly underneath that minimum, we have an intercept on the derivative. And we can put a hole there. And then it can keep going up like that, something like that. All right. Now, this is just an approximation of what the graph looks like. If you got 70% or so on that applet that practices drawing the derivative, then that is plenty good. All right. If you can get the basic shape, yours goes up where theirs goes up, yours goes down where theirs goes down, then you're doing exactly what I want you to do. All right. Okay. The last part we have to do is to use the graph of the velocity function that we just drew here, or the concavity of the original function, to determine where the acceleration is positive, negative, or zero. All right, well, first off, concavity will tell you when it is positive, negative, or at an inflection point, it's zero. We don't have any inflection points because when we do change curvature, it's at a corner, not at an inflection point. So we have negative acceleration here because it's concave down. So we have negative acceleration on the first section between 0 and 2. All right. Between 0 and 2, our acceleration is negative because it is curved down. All right. Like a frown. All right. And then we have positive acceleration over there between 6 and 7 because it is cupped up. Well, actually between 5 and 7 because it is cupped up. All right. So it's curved this way instead. All right. Okay. And then what about 0? All right. On the 0 one, when the velocity is 0, then the rate of change of velocity is 0. So the acceleration is going to be 0 in that same section there where it is not moving from 2 to 5. All right. Now we need to decide when it is speeding up and when it is slowing down. All right. So speeding up and slowing down. Okay, so we want to determine the time intervals where the object is speeding up or slowing down. So looking at the picture, remember that it stopped at the maximums, it stopped at minimums, and it stopped along horizontal sections. So it's got to be slowing down on this first section right here. So from 0 to 1.5, it's got to be slowing down because it's about to stop and it never changes curvature. So I would say it is slowing down on the first section between 0 and 1.5. Now, the next little section is a little kind of strange section that really can't happen to a real car. Well, I mean, it can, but it's not good for you or the car because what's happening here is he stopped. And then in order to get moving again, he's got to be speeding up and he's speeding up the whole time. And then he comes to an immediate halt, right? There's no slowing down section because there's no minimum again. It's just like slam on the brakes, hit a brick wall. So he's speeding up between 1.5 and 2. Which is really kind of a strange thing to say. You could say he has an instant slowdown at 2, all right, where he slammed on the brakes because he did come to a stop there. So at that instant, he stopped, but there was no slowing down. It was just immediate stop. And then over here, you could say that he is slowing down. Now, this is kind of weird too, because he's got an immediate speed up, but he's got to be slowing down on this section because he's about to stop again. So this isn't really a very realistic picture, but at any rate, so we've got this slowing down section between 5 and 6, and then a speeding up section between 6 and 7. He was stopped and now he's moving again. Okay. Let's take a look at another graph. This one is a more realistic graph and it's got some tangent lines on it to help you sort of predict what's happening at the different points and what it looks like. So we're going to answer the different questions. So when is it to the left of the origin and when is it to the right of the origin? Again, the entire graph, the whole thing is above the t-axis, which means that it is always to the right of the origin. And this time, unlike last time, notice that it started on the right side. So if we're using our example of the car on I-70, it started out already east of the intersection of I-25 and 70. It's already on the east side of that, and it stays on the east side of that. It does travel some east and west, but it stays on the east side the entire time of that intersection. So when is the time when it's at the origin? Well, it's never at the origin. It's never at that intersection. There's no intercept on the t-axis. To be at the origin, you have to touch the t-axis, and there are none. All right. Use the graph of the position function to determine the time intervals when the velocity is positive, negative, or zero. So, and we'll do this one and the next one combined, moving left, moving right, or stopped, since they mean the same thing. So the velocity is positive when it's uphill, and that means that it is heading towards the right or east. All right. So we have a positive velocity. It looks like heading uphill between 0 and 1. And then it goes downhill. So it's negative between 1 and 3. So it's headed west. Between 1 and 3. And then it is 0, which means it is stopped right there at 1. Scroll up a little bit to have a little more space. And then again at 3, it stopped at 3. And those are curled brackets right there to indicate single points. And then it speeds up again. So our slope of the tangent line goes uphill again between 3 and, well, what will we call that? 4.5, between 3 and 4.5, well, almost to 5. It's really uphill until it gets to 5. It's just very low. So it's really uphill between 3 and 5 again. And then at 5, it sort of goes horizontal. So we can say that from 5 on, it's stopped. All right. And this is a slightly more realistic type of graph. Right, with a very gradual change towards stopping. Notice it does not have a corner here. There's no sharp corner. So there's still a tangent line along this whole section in between where it had positive slope, positive velocity, and then it leveled off and became horizontal, which means it stopped. All right, which means it had to be gradually slowing down there. Now let's sketch the graph of the velocity on the same graph. So we're going to try and just do an approximation of it. So again, over this section right here, wherever it is looking like a parabola, it'll be linear. And we've got a spot right about here at 2 where it has an inflection point. And then we've got another one over here just past 4, where it changes curvature again. It has to change curvature. It's cupped up here, but it's clearly kind of got a downward curve to it here. So somewhere it's got to change curvature from up to down. Those changes in curvature correspond to changes in acceleration from cupped up, positive acceleration, to cupped down, negative acceleration. Okay. So let's take a look at drawing the derivative. It starts out with a positive slope. So we're going to start up here, and then it approaches the axis because directly underneath the maximum, we're going to have a t-intercept. So we're going to have a t-intercept here, and it's going to come down like this. Underneath our maxes and mins. We've got these intercepts. And then right here from 5 on, it's definitely on the line because the slope is 0, right? And then we've got to figure out what happens between 1 and 2. It goes negative and it gets more negative and more negative and more negative. And then notice how the slope starts to level back off again and come back towards horizontal. So the inflection point becomes the lowest spot on our graph. So we can put a point down here and come down, and then it comes back up like this. I kind of missed my point, right? And then it's going to have to do a similar thing on the other side, though probably not as extreme. So it's going to come up because the slope of the tangent line's positive until it reaches that inflection point, which will be a maximum, and then it comes back down. So this one is probably a lower rise up, comes up, and then it comes back down, and then it goes like this forevermore, all right? So that's sort of how I would draw the graph. Now, how low is this low spot? I don't know. I wouldn't know without doing some calculations on the numbers. How high should this spot here, this maximum be? Again, I don't know. If yours has this basic shape, that's good enough, all right? Now we're going to do where the acceleration is positive, negative, or 0. So again, looking at the original graph, we're looking for changes in concavity. So hang on while I get this to work. There we go. All right. So now we're looking at this. We want to look for changes in concavity. So the acceleration is going to be positive when it is concave up, negative when it is concave down. So positive when it's concave up, and we said our points were somewhere in here and here. And the inflection point is where that concavity changes. So between 2 and about 4.5, it's concave up. So that's positive acceleration. And then again, for the negative, where is it concave down? That would be between 0 and 2. And again, maybe 4.5 to 5, where it becomes horizontal. All right. So 4.5 to 5, and then it becomes horizontal. All right. Okay. And then where is it 0? It's going to be 0 wherever the other is 0. So it's 0 at 2, change in the inflection point, and it's 0 at 4.5, and then it's 0 on the horizontal section from 5 to infinity. There's no rate of change in the velocity. The velocity is 0, and so the acceleration is 0 as well. Right? Okay. How about speeding up and slowing down? So when we're looking at speeding up and slowing down, we're again looking for those high and low points and those horizontal sections. And right in front of 1, it's got to be slowing down. So it's slowing down from 0 to 1. And then it starts speeding up because it was stopped and now it's moving again. So it's speeding up between 1 and 2. And then it hits an inflection point, and that's where it stops speeding up and starts slowing down. So you have your foot on the brake, and then you stop at 1. Then you put your foot on the gas pedal, speeding up until 2. At 2, you take your foot off the gas, but the foot is not on the brake either. You're coasting at 2. Then you put your foot on the brake between 2 and 3. So you're slowing down again between 2 and 3. then you're speeding up again. So you put your foot back on the gas pedal and you're speeding up between 3 and about 4.5. And again, if you get close, if you call it 4.75, I would buy that. I would even probably buy 4. It could be anywhere in there. 4 is a little early, I think, but close. It's an estimation. And then, of course, it's going to be stopped and it's gradual. So it starts slowing down again at this after this inflection point. So between 4.5 and 5, it is slowing down again. Okay. All right. So we'll take a look at this graph right here. This is the graph, and we want to know, this is the graph of position versus time. So this is S of t. And we want to know which one of these red graphs is the graph of the derivative of it. So when we're looking at the blue graph, which one of these graphs down here represents the derivative of it? So the first thing to note is that the position is not changing here, which means the velocity should be 0, right? So if the velocity is 0, it should be on the axis, on the t-axis. That knocks out A, B, and D, and only leaves us with C and E. So we've already eliminated 3 of them right off the bat. All right. It's not moving. The position is staying the same. The last section is also horizontal, so the position is staying the same. So the velocity is 0. So this last section should be on the axis, but it is in both cases, so that doesn't help us eliminate anything. Then the next section is a linear section, so it should be a constant value velocity, but positive. And then the next one is a negative value of the velocity, but again, constant because it's linear, it's not curved. And that would be choice C. All right. Okay, let's now take a look. We're going to skip example 5 in the interest of time, and we're going to move on to examples 6 and 7. All right, so looking at example 6, we have a ball thrown downward with a speed of 8 feet per second. So it's thrown down, which means it has negative velocity. That's where the -8 in the formula is coming from. -16 is half of 32 feet per second squared. That's the acceleration due to gravity. It's always going to be -16 t squared if it's gravity and you're measuring in feet. And from the top of the 64-foot building, the initial position is 64 feet. That's why we're adding 64. So each of the coefficients here represents something. The first coefficient represents half of the acceleration due to gravity. The second one is the initial velocity. And the third one is the initial position, all right? After t seconds, this is the equation for the height above the ground. We want to know how long does it take for the ball to hit the ground, and then we want to find the velocity of the ball when it hits the ground. So we need to know how much time it takes so we know what the t value is to plug in for the velocity in the second part. So the first thing we need to do for part A is find when, well, when S of t is equal to 0. So we have -16 t squared minus 8t plus 64 equal to 0. The first thing I would do would be to do what? What would be the first thing you do?
And factor.
I would take out something. What would I take out?
8.
Yeah, I'd take out not just 8, but I'd take out a negative 8. I want my leading coefficient to be positive, and so I would take out the negative 8, and that would leave me with 2t squared plus t, oops, that should be minus 8 equals 0. Now, you can try to factor it, but in the interest of time, I'll tell you it doesn't factor. So what are you going to do since it doesn't factor? What's your only option? I know you don't like this, but you don't have a choice. Oh, come on, you know.
Polynomial formula.
Not polynomial. Oh, come on.
Quadratic.
Yes, you need the quadratic formula. And there's a song for that too, but I am not singing it for you because it goes to oh, what does the song go to? Twinkle, Twinkle, Little Star or something like that? I can't remember. Anyway, we're going to have to use the quadratic formula. So t equals the opposite of b plus or minus the square root of b squared minus 4 times a times c. The one place I do not abbreviate and do it in my head is when I'm doing the minus 4ac. I always write that part out because if I mess that part up, I change a real answer to imaginary and vice versa. That's a real big no-no and definitely something you don't want to do. All right. Okay. What about the next step? What are we going to do for the next step? Clean it up, right? So clean this up a little bit. Go ahead and do the arithmetic. So we have plus or minus 1. We have a double negative, which makes it a positive, which is a good thing. And this is 1 plus 64, which is going to give me 65 all over 4. So I have negative 1 plus or minus the square root of 65 over 4. But remember that this represents time. And what do you know about time for sure?
It has to be positive.
Has to be positive. It cannot be negative. So we can ignore the negative 1 minus the square root of 65 over 4 solution. And we can just look at the positive one, which is negative 1 plus the square root of 65 over 4. That's the time, how long it takes for the ball then to hit the ground where the position is 0. All right. Now we want the velocity of the ball when it hits the ground. So to get the velocity of the ball when it hits the ground, we need to take our equation and find the derivative. So to get the derivative, we're going to take our equation. Oh, I didn't need to copy it. I already copied it. And we're going to find v of t, which is s prime of t, which, remember the power rule. You take the 2, you bring it to the front and multiply by the coefficient. So you get negative 32t minus 8. And then we want to know what is the velocity when it hits the ground. This is the velocity at any point in time. The velocity when it hits the ground is going to be what we get when we plug in this negative 1 plus the square root of 65 over 4. So we have negative 32 times negative 1 plus the square root of 65 over 4 minus 8. And believe it or not, this does simplify quite nicely. The negative 32 over 4 simplifies to negative 8. And then I can distribute this across what's left. And this gives me 8 minus 8 square roots of 65. Did I do that right? Minus 8, and then the 8's cancel, and I get negative 8 square roots of 65, which is about, what is that? about 64.5. So negative 64.5 feet per second. So it's moving at a pretty good clip. All right. Definitely not something you want to be in the way of when it starts to fall. All right. Okay. All right, let's take a look at number 7. The position of a hummingbird flying along a straight line in t seconds is given by s of t is 3t cubed minus 7t. Determine the velocity of the bird at t equals 1 second. So the velocity of the bird is the derivative of the position function. So v of t is equal to s prime of t, which is going to bring the 3 to the front and multiply by the 3, which gives me 9t squared minus 7. And then I want to find it at 1 second. So v of 1 is equal to 9 minus 7, which is 2 meters per second. All right, it's given in meters per second. Okay. All right. And then the second one is, second question is determine the acceleration of the bird at 1 second. So to find the acceleration, we take the derivative of velocity. So the first derivative of velocity or the second derivative of position, which is going to give me an 18t. Notice the derivative of the negative 7 is 0 because the derivative of a constant is 0. So the power gets pulled to the front, multiplied by the 9, and you reduce the power by 1. So at 1 second, A of 1 is equal to 18 meters per second squared. Right? And the last one is find the acceleration of the bird when the velocity is 0. All right, so first we need to figure out when is velocity 0. So we take the velocity, which is our 9t squared minus 7, and we set it equal to 0. All right, then we can solve for t squared. We get 7 over 9, and we can take the square root of both sides. Normally, we would have to put in a plus or minus, but we know that t is time, so it's going to have to be the positive square root of 7 over 3. All right. And then we can find the acceleration at that point in time at the square root of 7 over 3, which is going to be 18 times the square root of 7 over 3, which is 6 square roots of 7 meters per second squared, which comes out to be about 15.9. All right. Okay, we can also do some population change and some changes in cost and revenue. We'll spend a little bit of time on population, but we'll probably spend more time on the cost and revenue of the time that we have left today. So population, again, we can approximate the population using that linear approximation function that we talked about at the beginning of class today. And remember, the linear approximation function is really just another way of saying the tangent line. All right. Now, population equations tend to be quite complicated. And so the tangent line, as long as you don't have a large change in time, the tangent line might be a good way to approximate it. And again, you're approximating it by taking the value at a particular point, multiplying by the derivative at that particular point times the change in time. All right. So that's basically what you're doing. So on the first problem, we have the current population of a mosquito colony is known to be 3,000 mosquitoes, which is definitely not a place I want to be. All right. If the change of the number of mosquitoes per unit time, the derivative is 100. Estimate the size of the population in 3 days, where T is measured in days. So if we're going to do this one, we're going to use the approximation function that we have up above, and we can say that P of 3 is approximately equal to P of 0, the original population, plus the change in time, which is 3 days, times the rate of change at time equals 0. Now, this isn't going to be a perfect amount. This is just an approximation. So when we approximate this, we end up with 3,000 for the original population. The rate of change was 100, so we end up with about 3,300 mosquitoes. Now, the next one is a more realistic formula for the culture of bacteria growing in a laboratory. So we've got this equation right here, which represents the number of bacteria at any point in time, where T is measured in hours. So we want to find the rate of change of the number of bacteria. Rate of change is just another way of saying find the derivative. Rate of change really, in essence, is the derivative. So we're looking for the derivative at that point. The first thing I'm going to do is to take the 3,000 and pull it out, and think of this formula as 3,000 plus, well, what would that be? 12,000? 12,000 T over T squared plus 100. So I distributed the 3,000. The reason I did that was I knew if I took the derivative of the constant part would go to 0, and I only need to focus on the second part at the back. So if I'm going to take the derivative of the second part at the back, I could in fact take the 12,000 off the whole thing and just think about keeping that as a constant outside the front. So remember, when we find the derivative, we have that constant multiple rule, which tells us that I can take any constant factor, the 12,000, and pull it to the front, and then do the derivative with respect to time of what's left over. So I want to take the derivative of this quotient. Remember, the quotient rule is going to give us f prime g minus g prime f all over g squared, where f is the numerator and g is the denominator. So I've got 12,000 hanging out at the front, waiting for the rest of this to occur. So the derivative of the numerator is 1 times the denominator, t squared plus 100, minus the derivative of the denominator is 2t, and the numerator is t, and it's all divided by t squared plus 100 quantity squared. And I can clean up the numerator a little bit. So I have 12,000 on the outside still. I have t squared plus 100 minus 2t squared over that quantity squared, which the t squared minus 2t squared is going to give me a negative t squared, which is going to give me just negative t squared. So I've got 12,000 times negative t squared plus 100 all over t squared plus 100 quantity squared. Now, did I make any mistakes? I did that kind of fast. So check my arithmetic and make sure that it looks correct. I think it is correct. Now we want to find the population change at 0, 10, 20, and 30 of the bacteria. by taking and plugging in 0, 10, 20, and 30. And in the interest of time, I won't make you go through and figure all of that out. I'll just give you what the values come out to be. N prime at 0 is 120 bacteria per hour. And then N prime at 10 turns out to be, where'd it go? 0 bacteria per hour. N prime of 20 turns out to be a negative 14.4 bacteria per hour. And N prime of 30 is a negative 9.6 bacteria per hour. All right. So first, the colony is growing and increasing, and then the rate of change of growth, population growth stops. It stops growing, but it's not losing bacteria either. And then it greatly decreases, but then the decrease, the die-off kind of slows down a little bit and comes back up. So it stabilizes a little bit. So the last question asks us to interpret the results. And one way of thinking about the rate of change is to think about the population as starting out and growing and then coming back something and leveling off, something like that. All right. So we started out with 120, and I'm graphing the rate of change here, not the number of bacteria. So this is N prime. All right. I'm graphing the rate of change. Okay. The last little section that we have is to talk about marginal cost, marginal revenue, and marginal profit. This is more an economic topic, but it is kind of an interesting application of calculus. Calculus does get used in business quite a bit. It's called business calculus. We don't do a lot with it in the normal calculus courses because we're more focused on engineering and science applications. But every once in a while, it's good to remember that it is used quite a bit in business and economics as well. In fact, there's a lot of calculus in economics. So marginal cost is the derivative of the cost function. Marginal revenue is the derivative of revenue. And of course, marginal profit would be the derivative of the profit function. Remember, revenue is what you take in, like the store, it's what goes in the cash register. Cost is what you had to pay to get the items in the store. Profit is the difference between the two. So your profit is equal to your revenue minus your cost. All right, okay. Now we want to talk about the marginal cost of an item. So when we talk about the marginal cost of an item, when you write MC of X, let's suppose we wrote MC5. MC5 is the cost it would take to make the 6th item. I've already made 5, that's why it's got the 5 in the parentheses, but the marginal cost of the 5th one tells me how much it will take to make the next one. So it would be the marginal cost with the 5 in it is giving me the cost of the 6th item. After I've already made 5. So marginal cost is sort of a cost of the next item after I've already made this many, all right? Marginal revenue is the same thing. It's the revenue for the next item after already having sold a certain number, and marginal profit is the profit on the next item after having already sold a certain number, all right? Now we can approximate these using that linear function, which ends up giving us the cost of the next item minus the cost of the previous item. And that will give us an approximation for the marginal cost. All right. That's one of the applications of the linear approximation function, which is just the tangent line. All right. So that gives us the cost. And again, this is when we make the change in the cost small, or the change in the number of items small, and small for us for a number of items is typically 1. All right. And that gives us this function right here. The marginal cost is approximately that value. All right. Okay. Let's suppose that we have a profit right here, attained from the sale of fish fry dinners. We have X fish fry dinners sold, and the profit is based on how many fish fry dinners we sold. We want to use the marginal profit function to estimate the profit from the sale of the 101st one. So if I'm looking for the sale of the 101st one, then I need to find P of 100. All right. So P of 100. Okay. So when I'm looking at P of 100, the marginal profit, I need to find the derivative of this equation. So the first thing I do is I find the derivative of that equation, which is going to give me a negative 0.06x plus 8. All right. And then I can plug in 100, and that will give me the marginal cost of the next item, which is the 101st one. So I've already sold 100. The next one I sell is going to be, I have no idea what that is. What, $2? So my profit on the 101st one would be $2. Okay. We can do a similar thing with the cost function. When we're looking at the cost function right here, we want to find the marginal cost function, which is going to be the derivative. The easiest thing to do is to rewrite this cost function with fractional exponents or negative exponents. So I've got plus 7 times x to the negative 1 plus 1/7 x squared. Notice that I took the 7 divided by x and I wrote it as 7 times x to the negative 1, so I can use the power rule instead of using the quotient rule. So the marginal cost function is just the derivative. So when I take the derivative of that, I'm going to pull the negative 1 to the front. And so I get the marginal cost function, which is going to be C prime, is going to be negative 7 x to the negative 2 plus 2/7 x. All right. Now you can also write this as negative 7 over x squared plus 2/7 x. You can write it either way. They're both correct. And then it says, find the marginal cost for producing the 13th food processor. These are food processors. So the food processor, that means I would find the marginal cost of the first 12. That gives me the marginal cost of the next item, which is the 13th. So I would plug in 12 squared plus 2/7 times 12. And when you do the arithmetic, you come up with about $3.38. All right, the marginal cost. So this must be like an automatic, a manual food processor, because food processors are a lot more expensive than that. And then it asks, what is the actual cost of the 13th one? So remember, the cost function gives you the cost of producing 13, not the cost of the 13th one. So to find the actual cost of the 13th one, you need to take the cost of 13 and subtract the cost of 12. And when you do that math using the actual function, you end up with $3.53. All right. So the marginal cost is $3.38. The actual cost is $3.53. All right. But marginal cost, remember that as you've already made some, the cost of the next ones go down because you've already paid for the overhead, you've already paid the insurance, you've already paid the workers. It's cheaper to make another one unless you have to hire more staff or buy more equipment. All right, so that's what the meaning of the marginal cost is.